Favored cardinalities of scales.
Peter Buch.
Abstract. In Western music history, the musical scales that were the most successful have 5, 7, or 12 tones per octave, respectively. Experimentalists have used 19, 31, or more tones per octave. A novel calculation is presented that yields these cardinalities, with a minimum of assumptions about scales, and without imposing a p-limit. The Riemann Zeta function plays a central role. Introduction. Scales are an important structural element of music. From prehistoric times until now, as music developed, the scales in use developed in parallel. And there is a long history of mathematical analysis of scales, starting with Pythagoras and with contributions of Avicenna, Ibn Sina, Zarlino, and hundreds of others in the modern times. Main stations of scale development are the pentatonic scale, which is still today the basic harmonic structure of very simple songs, the diatonic scale, which is what Western people sing when asked to sing a scale, the 12-tone equal temperament, 12-tet scale, which is the built-in scale of all modern keyboard instruments. The number of steps per octave, the cardinality, of these three scales are 5, 7, or 12, respectively. Beside these, microtonal scales with higher cardinalities have been used by experimentalists and studied by theorists. Cardinalities of 19, 31, and 431 have gathered special attention. The manifold and profound work done on this topic, e.g. the extensive bibliography given at 1, cannot be discussed here in detail. From the proportions of publications, as well as from the historic development, it can be deduced that some cardinalities seem to be better than others. In this article, I will introduce a new measure for how good a cardinality is. Conversely, this measure will allow to search for good cardinalities in a simple systematic way. The cardinalities favored by the majority of authors and by history will be reproduced to a high degree. Most of the literature mentioned deals with tuning, temperament, or intonation. This article is about cardinality. Though the question 1. These are the numbers n, 12 en.
2. Peter Buch.
Buch. Of cardinality and the question of tuning are closely related. Only the former is studied here, while the latter is left open. This is a short outline of my article. In Section 1, I sketch the well-known basic concepts about scales. I define some notions and introduce the basic problem. Section 2 presents something that may be called the standard theory of mathematical scale construction in the so-called 3-limit and 5-limit. The few examples in that section tell nothing new about scale theory. The purpose is to introduce the formalism that will be used in the following. In Section 3, I expand the standard problem and make a novel mathematical approach for solving it. The result is a list of good cardinalities. This article is interdisciplinary in the sense that it treats a music theoretical topic with mathematical methods. Sections 1 and 2 will bring nothing new to music theorists, although some of the well-known facts are presented in an unusual way. Then Section 3 will introduce some kind of mathematics unfamiliar to music theorists. On the other hand, mathematicians might welcome the short introduction to the topic in the first sections, whereas the last section might appear rather trivial to them. 1. Scales and numbers. In this introductory section, the well-known basic concepts about scales shall be sketched, and some notions defined. For a profound introduction, see E.G. Benson, 2, chapters 4 to 6. 1.1. Basic notions and definitions. Music is a matter of individual sensation and judgment. For this reason, it cannot be forced into a rigid mathematical formalism. There is no fixed set of properties that are mandatory for a musical scale, but at least there are some properties that tend to make a scale more pleasant. Thus, in the following, some notions are defined in a very general way, and not by rigorous mathematical definitions. They are supposed to represent the basics of the common-sense understanding of musical scales. The properties defined for intervals and scales are of a gradual nature. They may not only apply or not apply, but also may apply to some higher or lower degree. Despite of their lack of rigor, the definitions will turn out to be sufficient for deriving a result by mathematical means. The validity of the result is even underlined by the generality of this approach. Definition 1. A scale is an ordered set of pitches. It may have a periodically repeated pattern, e.g. every octave, or may not. Most studies on scale theory assume that scales have an octave periodicity, but this property is not needed in this article. Favored cardinalities of scales 3. Definition 2. Evenness of a scale shall denote its closeness to a scale with all steps of equal length. For example, an equal temperament 12-tone scale has the greatest possible evenness. A diatonic scale in just temperament is less even, as its step lengths vary from 15/16, 112 cents to 8:9, 204 cents. There are two reasons to aim for evenness. First, for the richness of music, scales shall have a sufficient number of different tones. And for being perceived as different, even in short notes, consecutive tones of a scale shall pitches that are not too close. The two aims of tone multitude and tone discriminability meet in the aim of evenness. Second, transposing pieces on fixed pitch instruments is greatly facilitated with even scales. This was the main reason for inventing 12-tet. Definition 3. An interval of two tones is consonant if their frequencies have a ratio made up of small integer numbers. Lower degrees of consonance are present if the ratio contains greater integers, or if a consonant interval is detuned a little. Though this classical definition of consonance has its limitations, there is no other definition that is as widely accepted. Definition 4. Harmony of a scale shall mean that many pairs of its tones form consonant intervals, and that at least the simplest consonant intervals appear in the scale. Lower degrees of harmony are present if the intervals are less consonant, or if the number of consonant pairs is low, or if simple consonant intervals, octaves, fifths, fourths, major and minor thirds, are missing. Note that this definition does not refer to intervals generating a scale, but to intervals actually appearing in it. The scales considered here need not be generated by a set of intervals. Certainly, it is possible to define numerical measures for evenness, consonance, and harmony. But this is not done as it is not necessary here, and thus the problem is avoided if such measures really represent the human sensation about these notions. 1.2. The scale construction problem. It is a general aim to construct scales that are both even and harmonic. But the two demands of evenness and harmony cannot be fulfilled perfectly at the same time. A just-tempered scale contains a lot of consonant intervals, and some dissonant ones, which cannot be avoided completely, e.g. Wolf intervals, and thus is well harmonic, but its steps are only approximately, albeit sufficiently, equal. An equal-tempered scale has perfectly equal steps, but the intervals it contains can only be approximately consonant. This is because, e.g., octaves, frequency ratio 1:2, and fifths. 2/1 cent is defined as an interval length such that a perfect octave has 1,200 cents.
4 Peter Buch.
Frequency ratio 2:3 are incommensurate. One cannot find a common measure, which is a smaller basic interval 1, b, with a real number b. 2 equals bn and 3/2 equals bm, 1. Thus, constructing an even and harmonic scale means finding a compromise between the two demands of harmony and evenness, and find ing approximations to equations like EQ1. There are, at least, two different ways of construction. Construction. The first is an approach originating from harmony. Starting with an empty set, tones are added one after another, making sure that every new tone forms consonant intervals with as many of the previous tones as possible. This can be formalized by using a set of generating intervals. The procedure is stopped when an approximately even series of tones is achieved. This is likely to be the way scales developed in history. In modern times, this procedure has been refined by group theoretical considerations 3 to 5. The second way starts from evenness, a basic step interval 1. B is taken to build a perfectly even scale with the frequency ratios 2, B minus 1, 1, B, B2, B3, If B is chosen luckily, this scale may contain a lot of consonant and almost consonant intervals and thus be more or less harmonic. These two construction schemes are equivalent in the following sense. If, in a harmonically constructed scale, all steps are replaced by an average length step, this will be a marginal change, as the scale was approximately even already before. This means that the resulting scale has the form of EQ2 and is still approximately harmonic. Conversely, starting from an equally spaced scale with approximate harmony, the tones may be shifted a small amount in order to get consonant intervals. So there is a correspondence between scales with higher harmony and scales with higher evenness. A common characteristic of such COR responding scales is the average step length. Definition 5. If a scale is sufficiently harmonic to contain octaves, or intervals very close to an octave, pseudo-octaves, and if it is sufficiently even that every pseudo-octave is divided into the same number of steps n, then n is called the cardinality of the scale. Clearly, this definition applies only to a subset of all possible scales. For all other scales, n remains undefined. N, if it exists, is the average length of the pseudo-octaves divided by the average step length. So corresponding scales are characterized by their common cardinality, if they have one, by definition 5. The difference between scales with favored cardinalities of scales 5. The same cardinality is their tuning. Tuning theory is in principle the theory of finding compromises between harmony and evenness. In the rest of this article, no preference will be given either to harmony or to evenness. In the history of music, many scales have been constructed, whether by intuition or by calculation. The most familiar are the pentatonic, the diatonic, and the chromatic scale with a cardinality of 5, 7, or 12, respectively, but also microtonal scales 2, ch6, with 19, 31, or more steps per octave have been studied and eventually used. The aim of this article is to investigate which the preferred cardinal idioms of scales are, regardless of the specific tuning of the scales. The reasoning is solely based on the assumption that the scale shall be even and harmonic as defined above. 2. Solutions for small factors. 2.1. Factors 2 and 3. Equation system 1 can be rewritten as
3. Q2 log 2 is gelijk aan Q3 log 3 is gelijk aan 1 log b.
with integers q2 equals n and q3 equals m plus n. 1. B is the average step interval. The logarithms may be taken to any base, since a change in the base makes the terms change by a common factor. Frequently, a base of 2 is taken, making log 2 is equal to 1 and thus measuring intervals in units of octaves. But octaves shall not be treated in a preferred way here. In the following, log shall denote the natural logarithm, base e. The goal is to find solutions q2, q3. With such a solution, 1/log b will arise. For this reason, the rightmost side of the equation is put in parentheses. Note that there are no integer solutions to EQ3, but there are approximations in the shape of near integer solutions. One such solution is given by 4, Q2 equals 7, Q3 equals 11.0947375 is almost equal to 11. It tells that a scale can be constructed with 7 steps per octave and, on average, Q2 equals 4.0947375 steps per perfect fifth. A number of 4-step intervals in this scale can be made perfect fifths, but not all. As 4 steps are, on average again, too short for a perfect fifth, there must be 4-step intervals, at least one per octave, that are shorter, flatter. For example, consider the well-known 7-step tuning. E 5-6, 15-16, 1, 9-8, 5-4, 4-3, 3-2, 5-3, 15-8, 2, 9-4, 5-2, E. E A B C D E F G A B C D E E. This shall only serve as an example, and the way such ratios are found shall not be discussed here. This scale is octave periodic. Every 7-step interval is a perfect octave. There are many perfect fifths in it, but
6 Peter Buch.
Also inevitable shorter four-step intervals, such as B, F, 45:64, diminished fifth, and DAA, 27:40, flat fifth. Another scale based on solution 4 is an equally spaced scale as in EQ2 with B equals 7 square root 2. Here, every fifth is flatter than perfect. Another solution to EQ3 is 5, Q2 equals 6.838045 is almost equal to 7, Q3 equals 10.838045 is almost equal to 11. It represents the same near integer approximation as EQ4, but is tuned to perfect fifths, as Q3 minus Q2 equals 4 here. By this, it is possible to construct a scale with all fifths perfect. Now, as Q2 7, the last two examples were rather unusual. They demonstrate the generality of the approach in this article. Article. Better than the previous approximations to EQ3 is the well-known near-integer solution. 6, Q2 equals 12, Q3 equals 19.0195500 is almost equal to 19. With a basic interval of 1, B equals 1, 12 square root 2 we get an equal step scale, EQ2, where 12 steps form an octave and 7 steps form an approximate fifth, because 7.0195500 steps are a perfect fifth. This is the familiar 12-tet scale. A series of approximations to EQ3 with increasing precision can be found by the continued fraction expansion of log 3/log 2 ch5. If a scale is based on a solution of EQ3, and if Q2 is a near integer, the scale will have a well-defined cardinality. 7, n equals nth Q2, where nth x is the nearest integer function, which maps a real number. X to the nearest integer 3. 2.2 more factors. For high degrees of harmony, see definition 4, scales will have to contain more kinds of consonant intervals, e.g., fourths, 3:4, major thirds, 4:5, and minor thirds, 5:6. In order to take these into account, EQ3 has to be extended to these larger factors.
8. Q2 log 2 is gelijk aan Q3 log 3 is gelijk aan Q4 log 4 is gelijk aan Q5 log 5 is gelijk aan Q6 log 6.
Given near integers Q2, Q3 that satisfy EQ8, there are near integers. Q4 equals 2Q2, and Q6 equals Q2 plus Q3 that do so too. The equation system could be restricted to prime numbers before searching approximations. But this 3. The definition of nth x in the middle between integers is of no interest here, because Q2 is a near integer. Favored cardinalities of scales. 7. 0, 1, 2, 3, 4. Is not necessary. Moreover, leaving the composite integers in the equitions will give a higher representation to smaller primes, as they appear as factors more frequently. In order to find approximate solutions for EQ8 visually, the number bears 1/log 2, 2/log 2, 3/log 2, 4/log 2 are marked on the axis of positive real numbers x, the numbers 1/log 3, 2/log 3, 3/log 3, 4/log 3. On a second copy of the axis, the numbers 1/log 4, 2/log 4, 3/log 4, 4/log 4. On a third copy of the axis, and so on, see Figure 1. The values of x, for which marks on the different axes nearly coincide, correspond to near integer solutions Qn to EQ8. So the 12th mark on the log 2 axis is very close to the 19th mark on the log 3 axis, cf EQ6, the 24th mark on the log 4 axis, of course, the 28th mark on the log 5 axis, and the 31st mark on the log 6 axis. All of them near x is almost equal to 17.3. This describes a scale where the frequency ratios of 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6 are represented by 12, 19, 24, 28, 31 steps, respectively. One step corresponds, at least on average, to the ratio 1, b with 1/log b equals x. This means 1, b is almost equal to 1 minute and 1.059 seconds, a chromatic semitone. So the 12-tet scale is not only based on a solution of EQ3, but also on a solution of equation system 8. Now, how can all such coincidences of axis marks be found in a more systematic way than just by eye? As a first step, in order to allow for near integers, the marks of figure 1 will be replaced by some kind of fuzzy marks. This is done by a function that marks all integers in a more tolerant or diffuse way, a not yet further specified periodic function f(x) that has peaks of some width at every integer valued x. The x-scaled functions f x log 2, f x log 3, f x log 4, f x log 5, f x log 6 are displayed in figure 2 and have peaks at the marks of figure 1. The function at the bottom of figure 2 is the sum of the above functions. 9 f x equals x6.
n égale 2.
F x log n. At any x where peaks of different functions f x log n coincide within the peak width, there is an especially great value of the sum function f x. The more peaks coincide, and the closer the coincidence is, the greater f x will be. So the procedure for finding good coincidences is finding local maxima of the coincidence function f x, which are, in some way, significantly high. Every peak of f x log 2 is accompanied by a peak of f x log 4, which is half as wide, and wherever peaks of f x log 2 and f x log 3 coincide, there is a narrower peak of f x log 6 with them. In this way, peaks of f x involving small prime numbers are higher and narrower than others. This would not be the case if the composite factors had been eliminated from EQ8. It is a desired effect as it reflects the higher importance of the simpler consonant intervals in a scale. Favored cardinality. (3.1) Giving up any p-limit. A scale or a set of intervals is called to be in the p-limit if p is the greatest prime number appearing in the frequency ratios. So equation 3 represents the 3 limit and equation 8 the 5 limit. Now the next step is to give up any artificial p-limit and extend our calculation to all frequency ratios 1, n. The goal is to find some x such that 10, x equals qn log n equals 2, 3, 4, 5, 6, 7, 8, with appropriate near integers qn. For a suitable coincidence function is 11 f x equals x infinity.
n égale 1 en f x log n.
The new n equals one term of the sum can safely be added because it is a constant f 0 and does not change the positions of the local maxima of fx. The factor 1/n sigma is new as well, unless sigma equals 0, and has, with a positive sigma, a twofold purpose. First, it can ensure convergence of the infinite sum. Second, it gives less weight to greater n. The latter effect can be regarded as a gentle replacement for the harsh cutoff by a p-limit. As an integer marking function is taken, 12 f x equals cos 2 pi x, which has peaks f x equals 1 for all integer valued x. It seems to be a very poor integer marking function because of the wide peaks of the simple cosine function. This will be discussed later. With this f x, the coincidence function can be transformed as follows. F x equals x infinity.
n égale 1 en sigma 13 cos 2 px log n
Equals x infinity.
n en sigma ri 2 pi log n
Equals x infinity.
n en sigma ri en 2 pi
Equals x infinity.
n en ri n sigma z 2 pi ri zeta sigma z 2 pi.
For readers who are not familiar with the following mathematics, may skip one page of text and continue at the paragraph marked by an asterisk. The function f x of section 2 will just be replaced by a different f x. Favored cardinalities of scales 11. Here Re denotes the real part of a complex number and zeta is the complex-valued Riemann zeta function 5, whereas the infinite sum converges only for sigma or 1. Asterisk the problem of finding coincidences in the Qn/log n equals 2, 3, 4, 5, is now translated into the simpler task of finding local maxima of Re zeta, sigma plus 2x, as a function of x, with a fixed sigma. Figure 3 shows f, x, and the axis of figure 1 for n equals 2, 3, 5. The correspondence between local maxima and coincidences can be seen easily. A value of 1/2 for sigma has been chosen just for convenience, but it can be shown that the position of the very high local maxima is almost the same for a wide range of of of
Sigma values.
The low quality of the cosine function as an integer marker, as noted above, is amended by the fact that f, x, is a sum over all integers, not only primes. Thus, there is not only a term for n equals 2, but also for the powers of 2, n equals 4, 8, 16, which have narrower maxima which add up at the maxima of the n equals 2 term and cancel out elsewhere. By this, the n equals 2 maxima are sharpened. 3.2. Finding good approximations. Now, what are the significant local maxima of f, x? A look at the function shows that the peaks tend to get higher for greater, positive, x, with a decreasing slope. That is why significance should not be defined by a constant threshold. For this reason, the heights of the local maxima are measured relative to the dotted line in Figure 3. The dotted line, growth curve, is an empirically found smooth function that approximates the growth of those local maxima that are greater than the ones before them. 0.6. A local maximum shall be considered significant if it reaches 95% of the growth curve. This is an arbitrary threshold value for the time being, but it will turn out to give sensible results. Every high local maximum of the zeta function is located very close to one of the so-called gram points 7 gk, k equals -1, 0, 1, 2, 8. The gram points, scaled down by a factor of 2 pi to match the definition. 5 named after Bernhard Riemann, 1826 to 1866, 6. Mathematician, not to be mistaken for Hugo Riemann, 1849 to 1919, musicologist. The zeta function was first introduced by Leonhard Euler, 1707 to 1783, who also invented the tonnets, but was unaware of the connection between zeta function and music theory. So, Riemann 6 equals Riemann, but Euler equals Euler. 6. The empiric growth curve is 2,3 exp, p3 theta, 2 pi x, where theta is the derivative of the Riemann-Siegel theta function. 7. After Jürgen Gram, 1850 to 1916, Danish mathematician. The gram points gk are defined by im zeta, 1, 2 plus ik, equals 0, re zeta, 1, 2 plus ik, 6, is equal to 0. 12.
Peter Buch.
1, 2, 3, Solutions of equation 10 of x are marked on the axis at f, x, equals 0 in Figure 3. Furthermore, the marks at the significant local maxima are labeled gk/2 pi. One can see that significant local maxima only appear at gram points. The value of f, x, at a significant local maximum is almost the same as f, gk/2 pi. Insofar as in the resolution of Figure 3, the labeled gram points cannot be distinguished from local maxima. So for finding the significant local maxima of f, x, it is sufficient to evaluate the function at the gram points, which are easy to calculate. In the following, the role of the significant maxima of f, x is taken over by the gram point values. Table 1 lists all significant maxima by the 95% definition up to x equals 2000. The entries up to k equals 32 are covered by Figure 3. The first 4 columns show the gram point index k, its position, and f, x, as an absolute value as well as relative to the growth curve. Further columns show the near integers qn for the primes n equals 2, 3, 5, 7. The greater f, x, is, the closer the qn are to integers, and the better an even and harmonic scale can be built in which night, qn, steps represent an interval of 1, n. The table also shows that the smaller primes tend to have better approximations. Octaves are always approximated well. This has not been a mandatory precondition in our deduction, but it comes from the natural importance of the prime factor 2. The cardinalities n equals night, q2 in the table are 1, 2, 3, 5, 7, 12, 19, 31, 41, 53, 72, 270, 311, 342, and 494. This is a short discussion of the individual rows of Table 1.
14 Peter Buch.
K equals 1, N equals 1. The first row represents a scale of octaves only, the only possible scale in the 2 limit. It is very regular and does not suffer of incommensurateness. But there are too few tones to make real music. K equals 0, N equals 2. In the second row, fifths are added to form approximate half-octave steps. K equals 2, N equals 3. This approximation represents the different kinds of triads, which are very simple scales. K equals 7, N equals 5. With the local maximum at x equals 7.26, real music begins. The pentatonic scale is the first to have enough tones to form pleasant tunes. K equals 13, N equals 7. The x equals 10.04 maximum tells that a cardinality of 7 can make good scales. So it is no surprise that the 7-step diatonic scale has been very successful. Western music is based on it. Some aspects have been discussed in subsection 2.1. K equals 32, N equals 12. The x equals 17.34 row of table 1 represents a 12-tone scale, cf EQ6. The importance of this cardinality is well known. K equals 63, N equals 19. K equals 125, N equals 31. These two rows describe microtonal scales with 19 and 31 tones per octave, which have been studied by many authors. K equals 182, N equals 41. Studies on 41-tone scales are very rare. What is a surprise with regard to the good quality of this approximation? 43-tone scales are mentioned much more frequently, though at n equals 43 f, x has a relative value of only 76.1%. K equals 255, N equals 53. A division of the octave in 53 steps was already discussed by Isaac Newton. K equals 378, N equals 72. The next approximation with Q2 is almost equal to 72 is of special interest, as 72 is a multiple of 12. So a 72-tone even scale can be used not only for approximating just intonation to a high degree, but also for reproducing the chromatic 12-tone scale, which it contains 6 times. The 72-tet scale has been explored by various authors. K greater than or equal to 1934, N greater than or equal to 270. While 72 tones in an octave can still be well distinguished by the human ear, there is no question that 270 or more tones, as in the last 4 rows of Table 1, are too many. These and the further, unlisted, solutions are only of mathematical interest. Conclusion. The essence of the entire Table 1 and of this article is that 5, 7, 12, 19, 31 steps per octave are all good approximations to the scale construction problem, whereas the numbers in between are of less quality, in a very general manner. I have obtained this result from only 2 simple assumptions about scales, harmony and evenness, without limiting the prime factors involved in the ratios and consonant intervals. The explicit construction of a scale has not been necessary. Favored cardinalities of scales 15. For this, the question of how to tune the 5, 7, 12, 19, 31 tones has been left open. The cardinalities found to be good are not new, but well known. This confirms the validity of the novel calculation presented here. To my knowledge, this is the first time that evidence for good cardinalities is found without referring to particular tunings. References. 1. Stichting Huygens-Fokker, Tuning and http://